I'd like us to look at a particular kind of wave superposition called standing waves. Standing waves occur when I have two waves that are coming at one another from opposite directions. So let's take a look at this little simulation right here. The blue and the red represent a right and a left traveling wave, and they're passing right through one another. The black curve represents the net wave amplitude, and notice what's happening to the net wave amplitude. It develops peaks and troughs which stay stationary, in the sense that they get bigger, but they don't move left or right. They just travel straight up and down. Now, there are more peaks and troughs that result here because as the blue and the red curves start overlapping with one another, then there are more crests and troughs that can overlap. But the central feature of a standing wave is that it's oscillating up and down, but doesn't move left to right. It just becomes like a jump rope that's being oscillated up and down, like when you play jump rope. So standing waves are the thing that are going to result from two oppositely traveling waves, and we're going to do the math of taking these individual traveling waves y1 and y2 and computing what is y total. Y total in the simulation is what's shown in black. And again, the feature of a standing wave is that the peaks and troughs of the black standing wave don't move left to right, they just oscillate up and down. So let's do the math. Let's actually say y1 is a sine kx minus omega t, and let's say y2 is a sine kx plus omega t. We're going to compute the sum, and so that's just y is equal to y1 plus y2. And we're going to use the same trig identity that we did in considering constructive and destructive interference, namely that the sum of these two sines is twice the sine of the average plus times the cosine of half theta 1 minus theta 2. In this case, theta 1 is kx minus omega t, theta 2 is kx plus omega t. What we find is that the total wave is twice a sine kx times cosine omega t. This is a funny thing because this is not a traveling wave. It can't be a traveling wave because it doesn't depend on the argument kx minus omega t. There's a sine kx, that's for sure, but it doesn't have any time right here in the argument of this sine function. Here's a cosine omega t, that could become part of a traveling wave, but because there's no kx in that argument, it's not a traveling wave. This is something that's changing a long distance and oscillating up and down in time. What does that mean? Well, we'll take a look in a minute. But it's called a standing wave for reasons that you'll see. The form of a standing wave, again, is twice a sine kx times cosine omega t. At any time whatsoever, you'll have this thing be 0 whenever k times x is a multiple of pi. So n can equal 0, 1, 2, 3, and so on. So what that means, if we were to watch this elapse over time, is that this would look a little bit like a guitar string. I'd have so-called nodes, places where there's no rise in the coordinate y, and the whole thing is oscillating up and down because of this cosine omega t. It's oscillating in time, up and down. So the antinodes occur when that sine function is not 0. Nodes occur when kx is equal to n pi, n is some integer, or if you think about k is 2 pi over lambda, that's the same thing as nodes occur whenever n is equal to a multiple of half of a wavelength. There are also locations where y of x and t is oscillating up and down, and that's because of the cosine term. And when sine kx is equal to 1, these oscillations are maximal. In other words, it's oscillating up and down everywhere, like here or here. But those oscillations are the biggest at places called the antinodes, and those occur halfway in between all the nodes.